Today we will talk about Kalman filter, which is the optimal observer for linear systems. We will talk about what observers are and how they apply to linear systems. And then we will talk about what exactly sets Kalman filters apart from the other observers. The basic motivation for studying Kalman filters is this. We need to know the state values at any given time in order to implement a control scheme. Now, it may not always be possible to measure the values of the internal states directly, and hence, in this case, we do the next best thing, which is to try estimate the state from the input and the output values. But there are issues with this because these measurements can be noisy. So, what a Kalman filter basically does is to make a good guess about the state values using all these noisy measurements and information. So, a Kalman filter extracts useful information, which is essentially the state values, from uncertain noisy data, which is the input and the output values, using some limited knowledge, which is the process model. And how it does that is by combining the information available from both sources, which is the measurement and the process model, in the best possible or the optimal way. Now, we will talk about how it's the optimal observer, or in what way it is the optimal observer, later in the slides. To begin with, let us just talk about the state system, the state space model of a linear system, which is given by x dot equals ax plus bu, which is the state equation, and the output equation, which is y equals cx. Here x is the state where the state matrix, u is the input matrix, and y is the output matrix. Now we have some information available about these matrices, which is the output and the input matrices. We know what the output matrix is since we can measure it. And we know what the input matrix is since we're the ones who are applying the input to the system. So we have information about these two, but it may not be the complete information. So how we try get the values of the state is by estimating. So coming back to this model, we start off with assuming that the state is at some given location. We call this x hat, x with the hat. This is the estimate of the state. Now, we say we do not know anything else about the state. All we know is it is probably what we estimated. So we say that let's assume that is what the state value is, and then you plug it in this equation. So the equation will then be the derivative of x hat equals a times x hat plus b of u. We do not estimate u since we know u, since it's the input that we're applying. And then we plug in the estimate of x in the output equation and get an estimate of the output. Now coming back to the observers, our estimate at the next point in time, or we can even talk about it in terms of the time derivative, which influences its value at next point in time. So this, it's just this part, this with the part from the process equation is what we estimated. But the estimate is not correct, and we want to nudge our estimate towards the correct value, and hence we add this term, which is basically a correction term. So we say that we have been using this estimate to get our next estimate and to get an estimate of our output. Now we have no information about the state, but we do have information about the output. And so we do a comparison, so to say, between the output that we're measuring and the output that we're predicting using our estimates. And then we try use that difference to nudge this entire term towards the correct value of x. So basically, we take the difference between the actual input, the actual output and the estimated output. And then we multiply it by a gain factor, saying that this is the general trend, and then we multiply it by some multiplier to get a term that we can add to our predicted values to make it more consistent with what we're observing. And over here, we can get the value of y hat, which is the estimation of the output, using our output equation from this model. And we essentially get our y hat is equal to c times x hat. And as you can see in this equation for the rate of change of the state estimate, it's got two terms basically, which is the predicted term. This is the information we're getting from the model, and the correction term, which is the information we're getting from the measurements. And in this equation, we are not estimating the input and the output since we're directly getting them from the measurements. Now let us talk about the actual system model. The system model that we introduced for the linear system is basically an ideal system, and it does not account for noise. So let us talk about the system where we have accounted for noise. So we've introduced these two vectors, which are basically noise vectors. Here, W is basically a disturbance which is added to the plant. So it is essentially just unaccounted inputs or some disturbances that may have crept up in the plant and is giving us unexpected results because of addition to this particular equation. And then we talk about this vector, which is a noise vector, which is originated from the sensor noise, and hence it is a noise which is added to our output. Now we say that all the elements in W and V are noise variables and they're random variables. We will talk about how exactly we've modeled noise in the next slide. Okay, so let us talk about how the noise is modeled, which is essentially how each element of the vector W and V is modeled. So we say each noise variable is an independent, unbiased, white noise variable. It follows this model. So if we know this about the noise, we can draw some relations about the correlations, which is that the noise vector W at any time t1 and the noise vector W at any time t2, which is some later time, is, or some previous time, is given by this vector multiplied by an impulse function. Now this vector is basically an intensity vector, which basically says how much the intensity of the noise will be at with passage of time. The same, almost the same relation for the v vector. The only difference is that this matrix, the intensity matrix, is different for this noise vector. And we also know that the disturbance to the plant, which is W, and the sensor noise are not related in any way, and hence the correlation between them at any time is always zero. Now, keeping these relations in mind, we will now talk about the error, which is, now we're nearing the part where we get to the Kalman filter gain. Now, let us recap. We wanted an estimate of the state, but we also need that estimate to be good for it to be useful. So we say that we consider an error in the estimation, which is basically x tilde, which is defined as the actual state value minus the estimated state value. Now you need to know that we do not know the x value for the actual x value at any time. So this is a concept, but we cannot directly find it since we do not know this value. And now we talk about the error dynamics, which is the change in error over time. And how we do this is basically by differentiating this relation, which gives us x tilde dot is equals x dot minus x hat dot. And we substitute this for x dot using our process model with the noise term minus x hat dot. And this is the term that we get from our observer equation, which gives us the rate of change of the estimate. Now, we substitute the value of y using our state model with the noise inputs, and it comes out to be cx plus v. And then we group together these terms. We have a times x minus x hat, which is basically x tilde. The bu terms cancel. The w term goes here. And minus L times C times X minus X hat, which is again X tilde. And that is this leftover term of L times V, which is here. So our error dynamics is basically X tilde hat equals A minus LC times X tilde plus W minus LV. This here is the noise term, and this we get from our observer gain and our process model. Now that we've defined the error and how it changes with time, we want to talk about what we can do to minimize the error. And we want the estimate to be as close to the actual value of the state. So we want to minimize the variation in the error. We want the error to basically be equal to zero for in most, like we want the distribution to be focused mostly on zero, and we and hence we want to reduce the variance. So our cost function can essentially be defined as the sum of all variances of the error elements. So that's basically the variation of each term in the x tilde vector. So j, which is our cost function, is equals sigma of x tilde 1 plus sigma square of x tilde 2 plus sigma square of x tilde 3, so on till sigma square of x tilde n. And this is written here in a concise way in terms of the expectation of x tilde transpose into x tilde. This is also the trace of the covariance matrix. Now, a trace basically is the sum of all diagonal elements, and the error covariance matrix is defined as the expectation of the error into error transpose. Now, the error covariance term essentially relates the each error term in the x tilde matrix to another term in the x tilde matrix. So this is x tilde is basically an n cross 1 matrix, and x tilde transpose is a 1 cross n matrix. So x tilde into x tilde transpose is basically an n cross n matrix, and we are trying to find the expectation of each of these terms in the n cross n matrix. So we now talk about the variation of this covariance matrix with respect to time. So we basically just differentiate it with respect to time, and the differential it opens up with the chain rule. Now we substitute the value for x tilde dot from our error dynamics, which is basically x tilde dot equals a minus LC times x tilde plus W minus LV, which was the error term, and this came from the process model, and they're both post multiplied by x tilde dot x tilde transpose. So this term and this term result from this term, and then we basically take the transpose of the x tilde dot, which we got from the error dynamics, and substitute the values in here. So this is basically x tilde transpose since into a minus LC transpose. Since transpose of a times b is equal to b transpose into a transpose, that is basically the law that is followed here. So this term essentially consists of this term right here and this term here. And we want to take the expectation of this entire expression. So now we know that A minus LC is not dependent on any of the other terms, so we can consider just the expectation of the x tilde into x tilde transpose. This is what we did in this term as well. And we take the expectation of this entire thing, which, if you will notice, is basically the transpose of the other term. So this term, W minus LV times X tilde transpose, is equal to the transpose of X tilde times W minus LV transpose. Because transpose of this thing is equal to transpose of this thing, and transpose of X tilde transpose is equals to X tilde, which is right here, multiplied by the transpose of the first term, which is right here. So essentially these two matrices are transpose of each other. Solving it further, we see that this equation, the expectation of x tilde into x tilde transpose, is essentially just the covariance matrix as we've defined. And we simply substitute it in here. To calculate this value, we go into matrix manipulation and some calculations which I've not included here since we would not be able to cover it in the time given. But essentially, the expectation of this term boils down to a function of the error intensities and the gain of the observer. So substituting this value in here, we get this equation for the rate of change of the error covariance matrix, which is related to the process model, the observer gain, the current value of the error covariance matrix, and the noise model, which basically affects the intensity matrices of the noise. So now we talk like a brief recap of whatever we've done so far. We have found a relation which shows us how our estimate should vary with time. This we get from the observer equation. And from the previous slide, we have a relation which shows how our error covariance matrix varies with time, which is this relation. And now we come to the part where we determine the Kalman filter gain, where we minimize the cost function, which we defined as sum of all error variances, and we minimize it with respect to L, which is the next part that we will be looking at. So essentially, our objective function is J equals trace of epsilon, which is the error covariance matrix. And trace was essentially the sum of all diagonal terms. And it is subject to this constraint in epsilon, which we get from this relation. So we essentially reduce it to an equality matrix, which is H of epsilon equals 0. So this problem is a constraint minimization problem, and we reduce it to an equivalent unconstrained problem by adding the term of lambda into H of epsilon. So we add this term lambda into H of epsilon, to epsilon and reduce this to a new objective function, which we will now optimize with respect to L. We do this by using the first order necessary condition, which is the first differential of J dash, which is the new objective function, with respect to the gain evaluated at the optimum value, which is L star, equals 0, which gives us this relation. And from there, we calculate the value of the L star, which is our Kalman filter gain. And it turns out to depend on the covariance matrix, the output equation and how it's modeled, the value C, and V2, which is the error to the output equation. And now finally, to get the final Kalman filter equations, we substitute this gain. This is the Kalman filter gain, and this is what makes it the Kalman filter as opposed to any other observer, since this is the gain at which this cost, or essentially this cost, the trace of epsilon, is minimized. So this is the gain value at which our error variances for all terms in x tilde are minimized. So we take this gain and we substitute this back into the equations for error covariance matrix updation and the state estimate updation. So this essentially describes the Kalman filter. Thank you.